Welcome back, everyone, to the third day of the program. So first lecture is by David Schaich from University of Liverpool. So this is going to be the second part of the lecture, Lattice supersymmetric field theories. David, over to you.
Thanks, Anosh. And morning, everyone. There are some new faces in the audience that hopefully, at least if you're willing to take as given some of the stuff that we covered on Monday, then you should be able to follow along at least most of the main points. So to review briefly what came up on Monday, looking at this outline, we didn't seem to get very far, though not all these points are equal. We focused on some of the motivation, background, and formulations for supersymmetric lattice field theories, but really we're able to see some of these challenges that have been and are being overcome, as well as look at some of the opportunities for lattice studies of supersymmetric quantum field theories that arise upon overcoming those challenges. So specifically looking at the ideas for the various different reasons we might be interested in lattice studies of supersymmetric quantum field theories, and then several different aspects of the way that formulating quantum field theories in the discrete space-time of a lattice necessarily breaks supersymmetry, either from the super-Poincare algebra, from the perspective of the Leibniz rule, or from more simple-minded considerations of typical ways the different fields are discretized. But then what we got part of the way through was a clever way to preserve at least a subset of supersymmetries in discrete space-time for certain theories with sufficient numbers of supersymmetries. We're focusing on maximally supersymmetric n equals 4 super Yang-Mills in 4 dimensions. And probably not today, but in the final lecture tomorrow, or possibly my shorter research talk next week, we'll focus on some of the other, or turn our attention away from n equal 4 super Yang-Mills to some of those other possibilities, theories in lower dimensions, or with less supersymmetry, even adding some matter multiplets to n equal 1 super Yang-Mills and the challenges related to that. But the plan for today is wrapping up the formulation of lattice n equal 4 super Yang-Mills that preserves part of these supersymmetries, and then diving into and really focusing on what my main interest and activity is in this field, which is not the question of formulating these lattice theories in principle, but actually implementing them in practice and running them on computers to get some numerical predictions for whatever we can. So again, questions are encouraged throughout the talk, not just at the occasional breaks. I'll check in right now if there are any immediate questions arising from that recap of Monday. And since there were relatively few at the discussion session last night, I'm going to just go ahead and, yes, we do have one. That's going to, so that sign problem is referring to the algorithms that we use in these numerical computations. They tend to assume that the lattice action is real and positive, and that's a condition on them. So that's the exponential of minus s, so Feynman factor Wick rotated to Euclidean space, can be treated as a probability. When that is not the case, if the action is negative or even complex valued, then you lose that connection to probabilities, and that is known as the sign problem. And at least some more about that tomorrow, possibly much more depending on how the time goes. That's the short and simple statement. But a great question, since it is being flashed on this outline without explanation so far. And the point we got to at the end of the first lecture was actually writing down the basic lattice action for n equal 4 super Yang-Mills following this procedure of changing variables through the twisting formulation, which we were able to do in the continuum, and then map the twisted continuum theory onto the lattice. The lattice action looks essentially the same as that in the continuum. The only difference is I have this gauge link U in place of the gauge field. And these calligraphic D bars are meant to be interpreted as finite difference operators that connect fields at different lattice sites, different space-time locations, as opposed to the gauge covariant derivatives that we want to recover in the continuum limit. The various fields in this lattice action all have a nice set of transformation properties which are connected to the way the gauge invariance is maintained in the discrete spacetime, where any gauge invariant quantity needs to be expressible as tracing over closed loops in the lattice spacetime. And we'll have some illustrations to make that more concrete. This is all based on this geometric perspective of the fermions in the fields in the system, which came up just at the end of Monday's lecture, and the related discussions about these so-called Kähler-Dirac fermions that distribute the fermionic degrees of freedom among the so-called site, link, and plaquette variables. There is this one twisted scalar fermion eta that is identified with each site in the lattice. There are then 5 twisted vector fermions psi associated with each link in the same way as that gauge link, which is complexified to include both the gauge field and the scalar fields. The adjoint of that gauge link, now that it's complexified, those are independent variables. They connect the same sites in the opposite orientation, going either from n plus mu hat to n, or from n to n plus mu hat. Then finally, there are the remaining 10 fermions to get the full 16, can be called plaquette variables. They're associated with 2 displacements in the lattice structure. And just to get a little illustration of sites and links and plaquettes, we can go through some of the examples for illustration of terms that appear in the action on the previous slide once we apply that twisted scalar supersymmetry and expand all that out. One relatively simple term is a fermion bilinear connected with this adjoint gauge link. So if we say that we start from site n in the lattice, and we have then, say, the first field identified with that is a psi a, which will take n to n minus a hat. So that's psi a going to n minus, I'll just call that a hat. Then the u bar raises us back from n minus a hat to n. So we have that closed loop already, and appropriately the eta at the end is just identified with that site. So taking the trace leaves all the gauge transformations canceling out in the trace and gauge invariant there. Another quick example that's maybe a bit less trivial than just going down and then back again in each of the 5 directions. A is looking at a different fermion bilinear. So again, starting from site n, we have this psi b now, which will take us down to n minus b hat. Now there, instead of a u bar with a u, we would then go over to n minus a hat minus b hat. And then finally, the plaquette fermion closes that loop and takes this term back to its starting point, and tracing gives us gauge invariance. Now there is one issue that will seem obvious once I point it out, which is I reminded you that all these variables a, or indices a and b, are running from 1 to 5, whereas if we have a 4-dimensional theory like n equal 4 super Yang-Mills, and we have in mind a picture like this hypercubic lattice, we would only have 4 directions in which to go. So there is something a bit more subtle going on, which is that the discretization of the system has to be formulated on a particular type of lattice that has 5 links, 5 basis vectors corresponding to the bosonic degrees of freedom that span 4 dimensions of space-time in a even-handed symmetric way. Now, when motivating why we were setting up these complexified links in the first place, we got motivation for that by working first in 5 dimensions where there's an equal number of scalars and an equal number of components in the gauge field, and then dimensionally reducing. We can do that same sort of thing when now that we've discretized space-time, to figure out what lattice structure we need. If we have a hypercubic lattice, either in position or momentum space, they're dual to each other. But in momentum space, the dimensional reduction corresponds to setting one partial derivative equal to 0. So that's in position space projecting along some axis. Momentum space, that corresponds to a vanishing partial derivative. And to keep things symmetric, we actually impose the constraint that the linear combination of all 5 partial derivatives in all 5 of these momentum directions, that linear combination vanishes, and we have then a projection to 4D momentum space that is no longer a hypercubic lattice, but it looks more like this situation where this is as much as I can fit into a 2-dimensional slide. This is illustrating a 3-dimensional hypercubic lattice being projected into a 2-dimensional triangular lattice that can generalize to higher dimensions. So the triangular lattice in 2 dimensions is called A2 or A2 star. In 4 dimensions, we would have in position space this A4 star lattice resulting from this procedure, which is exactly what we need. It's a lattice with 5 basis vectors that symmetrically span 4 space-time dimensions. As a consequence of that, so it is a direct analog of the triangular lattice in 2D that's pictured here. Those 5 basis vectors are necessarily linearly dependent and non-orthogonal. But what this A4 star lattice gives us, in addition to the right number of degrees of freedom to match n equal 4 super Yang-Mills, is a nice S5 point group symmetry that's actually even larger than the hypercubic symmetries of the hypercubic lattice. And one of the issues I mentioned in passing just toward the start of the first lecture was the way that a sufficient amount of lattice symmetry, in particular hypercubic symmetry, can, in normal circumstances, guarantee the restoration of continuous Poincare invariance in the continuum limit. That was something we discussed and some of the caveats to that at the discussion session at the end of Monday. And this S5 point group symmetry of the A4 star lattice gives us also precisely what we need in order to recover this twisted rotation symmetry, the continuous SO4, that is the analog of the Lorentz symmetry in this twisted formulation. So looking at these 5 and 10 component twisted variables that we formulated in order to transparently match on to the complexified gauge links that came out of the twisting procedure, we know that there needs to be some way to decompose those into the representations of that SO4, this integer spin, guys, with the vector, pseudoscalar, and tensor representations, for example. The counting works out easily enough. And there is an explicit construction with this 5 by 5 projection matrix that reveals how those discrete lattice variables, psi A and chi AB, transforming under this point group symmetry S5, map onto the continuous twisted variables in the continuum limit. This is actually something that was pointed out by our last lecture yesterday, Mitat Unsel. Orthogonal projection matrix, it's transposed as its inverse, and there's one nice feature of it is that, or maybe not a nice feature, but a nice thing to observe from here is that as we go along the first 4 entries in each column, those are the basis vectors of the A4 star lattice that I mentioned. Not orthogonal, linearly dependent. If we add up the first 4 of those 4 component vectors, we can see that we get the negative of that 5th vector. And this is a way to sort of make things very explicit, give a concrete basis to that A4 star lattice and see how it maps onto the continuum degrees of freedom which is particularly important because it is the restoration of that continuous twisted rotation symmetry in the continuum limit that promotes the single twisted scalar supercharge that we're able to maintain in the lattice to the full set of 16 supersymmetries of the continuum theory. I won't go through the proof or the demonstration of that, which has been around for about 10 years, but we'll take this as a nice consequence that arises in part from just considering the symmetries of the continuum of the lattice system, the possible terms in the system that can arise even through quantum effects, and showing how the full symmetries of the continuum theory are restored in the continuum limit of the lattice theory. We will do just a bit of that consideration. So this isn't going.
Can I ask a question?
Yeah.
I'm
Before we go on.
trying to visualize in 5 dimensions, and
Well, it's still 4 dimensions, but with 5 basis
well,
vectors.
yeah, but you started. But anyway, no, you're analog to the triangular lattice. The triangular lattice has 6 neighbors, but they're in pairs by reflection. So then there's 3, and there's 1 redundancy between them. Is that the same thing here? There's really 10 neighbors.
Exactly.
You have reflection. Okay.
So it's d+1 neighbors, d+1 times 2 for the forward and backward in d dimensions for these A, D star lattices. So it does completely generalize to any number of dimensions you might care to think about. Well, you have an AD star or an AD lattice. You can't do this twisting procedure without 2 to the D supersymmetries. Yep, the 3-dimensional version is called the body center cubic lattice. It has 8 neighbors for each site. Or is it face centered cubic? It's the one that's regular, face centered. No, body centered. I was right the first time, so shouldn't second guess. Yeah, that's so stepping stone from A2 star, which is triangular, to A3 star, which is body centered cubic, to then A4 star, which is the one we need for our n=4 super Yang-Mills in 4 dimensions. Now, getting back to this question of going to the continuum limit, we'll just look at the basic line of argumentation without going through all of the details that are in the literature for those who are curious. The way we approach this is first to assume that there is some RG blocking procedure that we can do to this lattice theory to flow from the scale of the lattice spacing at which is defined out to arbitrarily long distances where the lattice structure becomes essentially invisible to the physics. And the question is, so we have to assume that there is such a blocking transformation that preserves the lattice structure as well as that supersymmetry, which is non-trivial, but it does turn out to be the case. And then we can consider how the system evolves upon flowing to those longer distances, that lower energy scale, and in particular, construct what's called this long distance effective action, the collection of all possible terms that obey the symmetries of the lattice system, and compare that to the naive lattice action that we have at the cutoff, and see what parameters there might be that would have to be tuned in order to match one of those onto the other. So the result is that almost every possible term that obeys the lattice symmetries is already accounted for in the lattice action. But this long distance effective theory allows for different couplings to appear, different coefficients to show up for each of those terms. At least in this way, before applying that twisted supersymmetry, the application of that could lead to a proliferation of terms from, for instance, acting both on the eta and on the u, you would get two terms from Q acting on that, both of which have to have the same coefficient by preserving that twisted scalar supersymmetry. So that's this sort of simplification that comes along by the symmetries of the system. Okay, so that we have been recording all along. I was worried for a moment. So from looking at the number of terms and not worrying too much about where they come from, we can count that there are, at this point, 5 parameters that we might have to fine tune in order to match up with the continuum theory that we want. Now, we've written 4 of those as alpha 1 through 4. The 5th is gamma, just numbers, coefficients. And by some trivial rescaling of fields and of the 't Hooft coupling, the role of 3 of those parameters can all be absorbed so that there's only one linear combination left in this first line, along with a second linear combination I'll just call gamma prime, showing up as the coefficients of these terms that are allowed by the symmetries of the lattice theory, but do not show up in the lattice action or the continuum action of n equal 4 super Yang Mills. Now, in order to say something about this second line, what we can note again from that same work where all this was done was that some of these terms, if we expand out that action of the twisted scalar supersymmetry on them and decompose these the complexified gauge links back into ordinary gauge fields and the scalar fields, these terms lead to things like scalar mass terms popping up, as well as cubic interactions among those scalars, which would lift the moduli space of the system. We don't want that in the continuum limit that we get out, even though it is allowed by the less restrictive symmetries of the lattice theory, that S5 point group symmetry, and the single twisted scalar supersymmetry as opposed to all 16. Fortunately, there is something we can say about this issue of the moduli space that has to do with the behavior of the lattice action, and in particular the supersymmetry of the lattice action under this twisted scalar supercharge. So there's a whole way of approaching this that I've largely skirted around that treats this twisted scalar supersymmetry essentially as a BRST symmetry and can make analogies with topological field theory to guide some of the thinking about this. Now, what we are working with is not a topological field theory, but it does have this similarity that we have this charge that annihilates the action, the twisted scalar supersymmetry, and any observable that is annihilated by this action is a Q invariant, can be considered a topological observable and analyzed semi-classically. And this is a consequence of just a simple calculation that is simple enough, I'll go through it on this slide. It's convenient to, again, do a bit of rescaling of the fields to put the lattice action in the form of, again, the Q exact piece plus that Q closed piece, and writing the Q exact piece. So if I flash back to, actually, this slide already had the Q exact piece, all of these terms in parentheses in the first line become that lambda. And by field rescalings, we can shift the gauge coupling, the Yang-Mills coupling, or equivalently the 't Hooft coupling, only onto that first Q exact term, moving it away from the Q closed term. If we then take the derivative with respect to that inverse coupling of the sum observable that is topological, then we get 2 terms. So the derivative brings down the argument of that exponential. We pick up the operator times Q acting on lambda, all of which is inside the path integral over the partition function. So we get the negative expectation value of that combination, and then taking the derivative with the denominator brings down another factor of the partition function, and two separate integrals, one involving the observable, the other involving the q lambda that comes down. Now, the expectation value of this twisted scalar supersymmetry acting on any observable vanishes upon doing this integration. And because q acting on this topological observable vanishes, or configuration by field configuration, we can rearrange that first term to be expressed as q acting on this combination of the observable of interest times that lambda. So again, we have an overall q variation of some operator, the expectation value of which also vanishes. So what that means is that all of these topological observables are independent of the coupling and can be analyzed through just a one loop perturbative computation in that limit of g squared going to 0, we coupling, and the result then holds independent of the coupling. No objections to that right now, so let's talk a little bit about how we would do a perturbative calculation in lattice field theory. This is something that has popped up in parts of Anna's lectures, so it wasn't a central focus of that, and it won't be a central focus here. This is some work by Anosh some years ago, Anosh and others, where even at tree level in perturbation theory, if we're just talking about the propagators and the vertices that give us the Feynman rules from which we build up Feynman diagrams, even those propagators and vertices themselves are sensitive to the fact that the theory is formulated in this discrete space-time. They feel the effects of the non-zero lattice spacing. So as an example, looking at the gauge boson propagator and Feynman gauge in the continuum, that's a very simple expression. A gauge boson with momentum k mu has a propagator 1 over k squared. And if I break that up and remind you that this k squared is the sum over all k mu squared, the components of the momentum in each direction, when we discretize space-time, those continuous k mu's get replaced by this sine function. So k mu squared becomes the sine squared of that lattice spacing times the momentum over 2 with a factor of 4 out front. And we can check that in the limit of a going to 0, so when the argument of that sine is very small, we can approximate the sine just by the first term in its Taylor expansion. So we get ak over 2, quantity squared. That cancels out that a squared there and the 4 and gets back to the continuum limit of this propagator. As a brief aside, based on that sort of way of looking at things, the calculation to one loop that was done in this work was able to show that all of the divergences that show up in lattice perturbation theory at one loop. So first of all of the Feynman diagrams that you obtain in lattice perturbation theory at one loop directly match onto the corresponding diagrams in the continuum theory. All of the divergences that show up in those diagrams occur in that limit when a times k is very small, and these sorts of sine functions can be expanded to recover the continuum results. So the divergences occur where the lattice and continuum results coincide. So at least at one loop, this is not this behavior is not guaranteed at higher loop levels, but at one loop, all of the perturbative results for n equal 4 super Yang-Mills map directly onto the lattice theory. In particular, that tells us that the beta function is 0 at that one loop level, even though that's not related to one of these topological observables that we were talking about to motivate these perturbative computations. One such topological observable of interest is, again, that lattice action. And if we take that and plug that in to compute the partition function, just the integral over e to the minus s, I will completely skip that calculation and just show the result. There are contributions to the lattice partition function from the bosonic fields, from the fermion fields, and from the ghost fields that come as a result of the gauge fixing we have to do for a perturbative calculation. The bosons contribute a factor of 1 over the 5th power of the determinant of these finite difference operators acting on the classical background fields. Set aside the details of what exactly that means, but just flash the result that then the integration over the ghost fields gives a single power of that determinant. Integration over the 16 fermions gives another 4 powers of that determinant. And the combination of all of those cancels out to unity, which is a reflection that the moduli space of the theory is preserved, or it was present at the classical level and is preserved, protected against quantum corrections to all orders in perturbation theory, thanks to this topological connection, this analogy to BRST invariance. So that, getting back to the question of the continuum limit of the lattice system, tells us that at least to all orders in lattice perturbation theory, we have to have gamma equals 0, because otherwise any non-zero gamma would correspond to the loss of that moduli space, the appearance of scalar masses and other nasty terms that we've now seen are forbidden. So if we make the assumption that the moduli space is also not damaged by truly non-perturbative effects like instantons, then that second line there drops out, and all that is left to get from the lattice theory to continuum n equal 4 super Yang-Mills with this twisted rotation group and all 16 supersymmetries is an appropriate tuning of this one remaining collection, this one remaining parameter appearing in a dimension 4 operator. So this is essentially the realization of the dream that we use to motivate the twisting procedure and the preservation of supersymmetry in the first place. You know, we went through in the first lecture the argument that completely breaking the supersymmetries would require roughly 10 parameters in to be fine-tuned to recover the correct continuum limit from a lattice theory without supersymmetry. That with an assumption that we don't have really empirical data on, takes it down to 1 parameter to be fine-tuned, and possibly the second parameter in the case if it turns out that these instantons do cause trouble in the lattice theory. And that is getting us just about to the end of the formal setup, just to tick off one of the assumptions that went into things, into that continuum limit. We relied on the existence of an RG blocking transformation that preserved all the symmetries in the geometric structure of the lattice system. There is at least one such option that was constructed as part of that work, where it proceeds much like the sort of blocking that Anna was talking about in her lecture yesterday for the Ising model. We take 2 of these gauge links that are nearest neighbors in the direction A that they are pointing. So we have those 2 gauge links, UA and UA. The blocking fuses those together into a single link that connects this initial site n to n plus 2 displacements in the corresponding direction. The same thing has to be done for the corresponding link fermions to preserve the twisted scalar supersymmetry that relates these. The site variables are left unaffected. There are 6 permutations of links and Lequette variables that come in that provide a blocked set of plaquette fermions that connect site N to the twice displaced site in both of those two directions, A, B. And so what we get is a system with twice the lattice spacing and a tunable rescaling factor C that comes in with either 0, 1, or 2 powers, depending on the number of indices that there are. We won't be doing anything with this RG blocking procedure explicitly, but it's nice to know that it does exist, that satisfies one of the assumptions going into that consideration of the continuum limit. So that is ticking off for the first block of the outline here. So I'm going to pause for any questions about sort of formal formulation of this twisted lattice system and the recovery of the correct continuum limit before getting into sort of practical applications and numerical computations. Not specifically. So this is not something that we are, not a concrete worry that we have. It's a limitation of the argumentation that has led to this claim that there's only this one parameter to tune. So this is looking for instantons is something that we can dream about doing in a lattice calculation. It's fairly difficult. Not to my knowledge, but my knowledge on that side of things is limited. And yeah, Simon Catterall is probably a better person to ask because he's been spending the last few years looking very closely at the 't Hooft anomalies that correspond to these sorts of Kähler-Dirac fermions, mostly without supersymmetry in these days, but there is a lot of subtlety in those non-supersymmetric Dirac-Kähler systems that relate to the symmetric mass generation and BKT transitions that we might hear about in some of the research talks. I don't know if any of that maps into the lattice N=4 super Yang mills. What I will say is at present, I have seen no reason to be explicitly concerned about these instantons. They remain a possibility that we can't rule out, that this conclusion that the moduli space is protected and that the continuum limit is simplified is perturbative, albeit to all orders in perturbation theory. Yeah, it's a nice connection to domain wall fermions is not one I thought about, and I will think about that when I'm not up here. Yeah, and that I don't think has been done to date. So anything else before moving on?
I'm confused about the effective action that we have started off with to move to the lattice action. So the different terms are coming just from symmetries.
Yeah, we're writing down every possible term that we can imagine constructed from the fields that are gauge invariant. They form these closed loops. They transform in representations of that S5, which is why they come in with those A and B indices. And then there's actually some more symmetries that I've not gone into. There are shift symmetries on the fermions, as well as a fun symmetry that's called ghost number. What that is going back to the twisting procedure, we combined the SO4 rotations with an SO4 subgroup of the SO6 R symmetry that leaves some R symmetry left over. In particular, there's an SO2 remnant that's a U1, and That's what's called ghost number for some reasons I forget. But different fields have different charges under that ghost number. And those all have to match up in the construction of these operators. So it might be a fun exercise to go through thinking about what possible combinations of all of the fields in the systems we can come up with, and which of those are forbidden by the symmetries which are allowed. I'll preview a little thing that this is only going up to dimension 4 operators. If we go to dimension 5, there would actually be no operators. All the possibilities would be forbidden by that twisted scalar supersymmetry. So the irrelevant corrections to this in the RG sense are coming in at dimension 6 operators. So in the context of, or the terminology of lattice field theory, they're order A squared effects in the continuum limit. And we will come back to that as we go to some actual practical numerical calculations with this setup. So I will head into that now. So we've seen some nice features of the formal construction of the system, a perturbatively preserved moduli space, a vanishing beta function at one loop, and the single logarithmic tuning. But that is not enough for us to be able to do numerical computations in practice. And in fact, it can even introduce obstacles to that, in particular, that nice quantum moduli space that we want to have in the continuum theory implies zero modes and flat directions in the system that make a numerical computation essentially uncontrolled or ill-defined. We have to regulate those zero modes and flat directions in order to have a controlled numerical calculation. And in particular, because we have those complexified gauge links that produce the UN gauge invariance rather than SUN that we started off with, we have zero modes and flat directions separately in both the SUN and U1 sectors of the full UN gauge group that have to be addressed separately, or both of them have to be addressed. So this is just an illustration of this kind of thing that can go wrong in a numerical calculation in the presence of these sorts of flat directions. So one thing that popped up toward the end of Monday's lecture was that in order to recover the correct covariant derivatives in the continuum, these lattice gauge links have to approach unit matrices with the continuum gauge fields identified as fluctuations around unity. And it's those unit matrices that provide just the partial derivatives in the gauge covariant derivatives. And due to these flat directions, as we do a lattice calculation, these link variables U are able to move far away from what they need to be in order to get that correct continuum limit. So I'm mentioning here Markov chain importance sampling in the rational hybrid Monte Carlo algorithm. That's something I can go on about for a whole separate lecture, and something that it sounds like Anna might not address in her lectures on lattice field theory. These are general methods in lattice calculations. And just to give you the view from 10,000 feet, the idea is in this Markov chain importance sampling, we want to sample sets of field configurations weighted according to the probability that they contribute to the path integral. This is where that sign problem comes up, that question from before, where the lattice action is providing the exponential, is appearing in the exponential factor that's interpreted as that probability. The idea of how to do this is, or the Markov chain approach to doing this, is to start with some field configuration, propose some change to the field variables, and then either accept or reject that change depending on how much the action itself changes. So there are many more details I can give, in particular related to this rational hybrid Monte Carlo algorithm, which is a way of proposing updates, proposing new configurations to sample based on the configurations that we already have. The really only aspect of the algorithm that we need to appreciate to interpret this plot is the idea that we are going through a series or a sequence of field configurations, each one obtained from the last. And the horizontal axis of this plot, what's being called here molecular dynamics time units, is related to the way that the hybrid Monte Carlo generates each configuration from the one before by doing some fictitious molecular dynamics evolution with random momenta in a fictitious time variable. And as that algorithm proceeds, getting a few thousand configurations, we can measure some observables, in this case, what I'm calling the Baldaceno loop, which is the Polyakov loop built out of these complexified gauge links. So it's the product of the temporal gauge link, so the link in the temporal direction along all of the temporal sites averaged over the spatial volume. That this is a topological observable. And for all lambda lat, we expect it to be approximately equal to 1, which is where the calculation started off here. And then as we went through the first few hundred iterations of this rational hybrid Monte Carlo algorithm, the Baldaceno loop did not stay around 1. It wandered off on this logarithmic scale to about 1 billion, 10 to the power 9, which is reflecting the gauge links appearing in the product wandering far away from where they need to be in order to get the right continuum limit. So this is a sign that the system is wandering away down those flat directions and causing trouble for being able to connect the numerical calculations to the continuum theory. So we have to regulate those flat directions in some way. And there's a straightforward, sort of naive way of doing so, which is just add a potential for the scalars that pushes or tries to encourage those gauge lengths to remain around the identity matrix where they need to be in the continuum limit. So taking that lattice action, adding some potential term with a tunable coefficient mu squared, there are as many options for this potential as we have creativity to come up with them and time to test them. Two that are in common use are shown here. And they differ in that this first one, which squares a trace, this is a double trace operator that tries to constrain the trace of the product UU bar. So that this is a nice gauge invariant quantity similar to psi A times U bar A. U goes from site n to n minus A, U bar takes it back, take the trace, it's gauge invariant. This encourages that trace to be near 1 after normalizing by the number of colors. Alternately, we can take a single trace of this operator UU bar minus the identity, which has the advantage of trying to separately push each eigenvalue of this UU bar combination to be close to 1, rather than the overall trace itself. You could worry in the first case that there's some very large eigenvalue going off in one direction that cancels a very large eigenvalue going off in another, and a flat direction could reappear through those dynamics. In practice, when we compare calculations with both of those potentials, they behave similarly. There's not really a dramatic difference or a reason to prefer one or the other. What both of them do, though, is explicitly break that single twisted scalar supersymmetry that we had left in the lattice system. The other 15 were broken by the lattice discretization of space-time itself. So the continuum limit now becomes slightly more complicated. We have this tuning of that parameter mu squared to 0 in order to restore now the twisted scalar supersymmetry. in order to get back all the rest, as well as that the physical moduli space in the SUN sector, that is a feature of continuum n = 4 super Yang mills. So we might worry that having broken with this scalar potential, the last supersymmetry that was available, in the worst case, we might go back to that situation where we had those order 10 parameters to have to tune to get to the continuum limit. Fortunately, things remain a lot better than that because we have the limit of mu squared going to 0, in which all of the supersymmetry violating operators are forced to vanish. This is, I guess, you could call it technical naturalness. It's at least spiritually related to that. It's a soft supersymmetry breaking that we have control over and can remove by dialing this parameter. So a way of monitoring the effects of this soft supersymmetry breaking and confirming that it is correctly going away in the continuum is to try to measure a Ward identity, see that it doesn't work because the supersymmetry has been broken, and then see how the violations of that Ward identity depend on the coefficient of the supersymmetry breaking potential. So what's being plotted here is a particular Ward identity that is twisted scalar supersymmetry acting on at eta UU bar. That was one of the extra terms that appeared in that long distance effective action, one that would have corresponded to scalar masses in cubic terms. And we see that the violations are bang on linear against this parameter. It sounds like there's a question.
Yeah, I have a question. I want to let you finish this and then I'll ask a question.
Yeah, the only last thing on this slide is an explicitly showing what this Ward identity actually is, that these two terms are meant to be equal. One of them is a fermion bilinear, and the other a product just of the bosonic degrees of freedom. So that is what's being plotted on the vertical axis. So I'll take the question now.
This is a technical question, which is there's other ways to live the flat directions in n = 4 Yang mills, which is when you go through some spatial periodic cycle, you twist the scalars so that there's no zero mode any longer, and you can, twist all the scalars simultaneously to some eigenvalues that do that. That usually preserves some of the supersymmetries. It breaks some of the stuff, but can that be done, or is that too expensive? Or
so
because things got converted into vectors, it's hard to figure out. But I would really like to know that, because that might clean up in some other ways, preserving supersymmetry.
We will actually be seeing a different way of lifting some flat directions in the next slide. Not that one, though. And I remember thinking about this some years ago, the idea that boundary conditions could be imposed to do this sort of thing. That was an idea that was in the air. It wasn't one that we got around to testing, in large part because that A4 star lattice makes the boundary conditions kind of a pain to work with. I think it can be done and can be explored. And it has not yet been, but it would be interesting to do so. And maybe someone else in the room would be interested to try that out based on the framework that is now available.
Thank you.
There's another question. Looks like. Maybe.
I don't know. Hello? Okay.
It's working.
Yeah, so I like to ask simple questions. Why do you have to do this at all? The action does not depend on this flat direction, right?
So if we don't do this, we get things like this.
I understand that, but I'm going to be even more simple-minded. So the action doesn't depend on this, right? So no matter what value you're at, you're getting the same sampling, right?
We are adding a potential to the action.
No, you are adding it, but I want to not add it.
If you don't add it,
I know it drifts,
yeah.
but the action does not depend. Well, I want the answer for first question. Does the action depend on this? I mean, that's what, look at it. In a normal theory, we keep the gauge variables. The action doesn't depend on it. Of course, we wander around that space. Now, in that case, we make them compact so they don't go off to infinity, they just keep circling around. So I understand your gauge links are not compact, right?
They're not.
So I mean, I understand that it's different in that respect. But what happens if isn't this good data up there? It may be inconvenient, maybe we should restart it, or what?
But what it is data that does not likely correspond to the continuum theory of interest. So this is a nice, well-defined statistical system. It has all these funny fermions and scalars and gauge bosons. If we want to say it's actually n equal 4 super Yang-Mills, we have to get a continuum limit out of it. And that is what is being broken by
these flat
this sort of
directions
behavior.
exist in the continuum limit, right?
They exist in the continuum
I
limit.
see, but they're being modeled incorrectly in the lattice theory. That's what you're saying.
Or the way that they behave in the lattice theory is taking us away from the continuum limit that we want. So it's the interplay of the flat directions in the lattice calculation. So this is a very good question to emphasize that we want these flat directions in the continuum theory. We want to get back to them.
But if I take the action, move it in this flat direction, the lattice action, and evaluate it again, don't I get the same number?
More or less, yeah.
No, more. I'm not asking more or less. Do you get exactly the same number or no?
Well, yeah, if it's a flat direction that you do, that's essentially the definition of a flat direction. It doesn't change
Exactly.
the action.
So I still don't understand why you actually have to fix it. I mean, maybe algorithmically you have to fix it, but
Yeah, if we want to interpret the lattice system that we have as n equal 4 super Yang-Mills, then we need to retain this continuum limit.
Let me answer it differently. If you actually go in flat dimensions in n equal 4 Yang-Mills and you ask what is the vacuum, it's not unique. It's a family of vacuum. So if you're averaging over all the vacuum, you're getting the wrong theory. You need to get one vacuum. And it's a vacuum where all the d-branes and the gauge symmetries is restored. Well, not just in the wrong vacuum, in a superposition of the wrong vacuum.
Yeah, that's a good way of rephrasing it. This
in the right vacuum fixes this.
Essentially, this constraint here that.
Well, normal gauge invariance, you have one vacuum and that's it. Here you have a family of vacuum. You need to pick the right one. Yes. No, but here you have a family of vacuum. N equal 4 is spontaneously broken symmetry with a whole bunch of Higgs mechanisms and masses and W bosons, and they are all zero energy states.
Yeah.
Yes.
Always many ways to answer a question, and that's a good one. Yeah, so essentially this condition up here is that vacuum, picking out that point on the moduli space that we're getting to. Good. So I guess getting back to something I mentioned in response to David's, there is another question. Good. Maybe I can repeat the question for recording and the remote participants.
I just wanted to know whether we can add a potential which can preserve supersymmetry, adding some fermion bilinears, and if it is not too computationally possible.
Yeah, so that is actually exactly what I'm going to talk about next, ways to do things a bit more cleverly. So the next, we will have time for today, is exactly addressing this question, which is rather than just sticking in a naive soft SUSY breaking potential, can we be more clever and stick in a supersymmetry preserving potential, or equivalently play with the boundary conditions to lift these flat directions in a healthier way in terms of supersymmetry. This becomes more relevant when we look at the other flat directions from the U1 part of that UN gauge invariance. So this U1 piece is actually, it's a non-compact UN, but the U1 part is compact, and the lattice experts in the audience may know that compact U1 lattice gauge theory exhibits a confinement transition that's related to monopole condensation. And yeah, I'll not go into any details really about what what the procedures are to observe or analyze this monopole condensation. It's related to counting the monopole world lines that are going through the cells of the lattice. There's a famous paper by Tom DeGrand and Doug Toussaint from more than 40 years ago showing how this can be done in a lattice field theory. It depends on the phase of the determinant of each link going around the plaquettes that are bounding the volume elements in the system. And when we do this for n = 4, it actually becomes tricky to do that sort of thing on the A4 star lattice. What we've done is worked with the A4 star lattice in a simple representation of a hypercubic lattice with a fifth link going along the backwards diagonal in that 4 dimensions, -1, -1, -1, -1, which is just a convenient representation of the A4 star lattice. This is how that would look in 2 dimensions for the A2 star triangular lattice compared to a 2-dimensional square lattice with a backward link. And when looking at monopoles, we actually do those based on the unit hypercubes. So we merge together some of the neighboring cells of the A4 star lattice that annihilates some pairs of monopole, anti-monopole world lines in those neighboring sites. That's a UV fluctuation we cannot worry about. What we get out of this is a measure of how many monopole world lines there are in this 4-dimensional volume as a fraction of the total number of plaquettes that we have. And if we look at calculations with various lattice volumes going along, values of that 't Hooft coupling around order 1, we see that this monopole density is 0 at weak coupling and then turns on and becomes non-zero around this lattice 't Hooft coupling lambda lat around 1, which is also the place where we see things like the Moduli loop that we discussed earlier falling down away from the 1 that we expect for all couplings. It approaches 0, approaching it more rapidly as the lattice volume increases. And the determinant of the plaquette similarly deviates from 1 heading down towards 0. This plaquette determinant is relevant as the simplest gauge invariant operator that is sensitive to the U1 sector of the UN gauge symmetry. So the overall conclusion based on this sort of behavior is that monopoles are condensing, which is giving us a confined phase in the lattice theory, which again is causing trouble when we want to connect that to continuum n = 4, which is not a confined theory. So this is a manifestation of problems with flat directions in the U1 sector. If we proceed as before, do a simple-minded supersymmetry breaking potential on that plaquette determinant degree of freedom that's sensitive to the U1 sector that cancels out actually in UU bar, then again, we can monitor ward identity violations. And what we notice, this is back from that same work in 2014, just looking at a very small lattice and scanning any values of both the mu-squared deformation that we had before, as well as this new tunable kappa parameter on the second SUSY violating potential. These ward identity violations are actually a lot more sensitive to varying kappa on the horizontal axis than they are to varying mu-squared, which gives the width of this band of different points going along the same amount of variation. Here we're looking at a different ward identity than before. This is violations of the known value for the bosonic action that follows from the lattice action as a whole being supersymmetric. So this was our motivation to go beyond the simple-minded SUSY breaking potentials and look at some of the more clever ways of constructing things, rather than implementing twisted boundary conditions. What we did was modify the moduli space of the theory, essentially modify the moduli equations, or the equations of motion for that bosonic auxiliary field D that we met on Monday. So in the blue curly brackets, this is the new change in this lattice action that is being done now to regulate the U1 flat directions. We add some arbitrary operator that transforms as a site variable under the gauge transformations. That gets added to the d bar u term that was what we had here in the original lattice action and the continuum action of n equal 4 super Yang-Mills. This modifies the equations of motion for the auxiliary field to include that operator with a tunable parameter g in addition to d bar u. And if we then choose this operator to be that Plaquette determinant -1, so trying to force the Plaquette determinant to be 1, where we want to have it to control that U1 sector, that lifts the zero modes of flat directions, and it does so by adding a Q-exact term to the lattice action, so it's manifestly supersymmetric. We are adding now another parameter, but it's also a nice feature of this setup is that because the U1 sector decouples in the continuum limit, we don't really have to worry about tuning this new parameter G, as long as we keep it at a sensible value that suffices to allow the numerical calculations to behave themselves. We can take the continuum limit, and when we take the continuum limit, that U1 sector as a whole will decouple from the SUN of interest. So this is looking at that continuum limit and comparing this improved action that has the Plaquette determinant deformation in the Q-exact piece of the action. Again, going back to the word identity violations that involve that fermion bilinear. The red points are what we got from the simple-minded way of just sticking in naive SUSY breaking potentials. Both of these fits here are going to 0 in the continuum limit. They are recovering the twisted scalar supersymmetry, but one of them is going to 0 much more quickly than the other on these log-log axes. So as the lattice volume gets larger and we approach the continuum limit, the improvement coming from this more clever way of doing things that preserves the supersymmetry is getting better and better. And in particular, I'll point out that the slope of this line on the log-log axes is approximately 2. So this is corresponding to the order A squared approach to the continuum limit. So lattice discretization artifacts vanishing proportional to the lattice spacing squared. And that is a reflection of something I said earlier regarding the long distance effective action, that there are no dimension 5 operators that are allowed by that twisted scalar supersymmetry. So despite this scalar potential still being present and softly breaking that supersymmetry, so we have non-zero values for the ward identity violations, in this setup, the supersymmetry is preserved well enough that we effectively have that order A improvement that the exact symmetry would provide for us. So this was a very fun result and a nice illustration of why it pays to think carefully about what's going on in the lattice system and not do necessarily the simplest thing, but work with these improved actions that have come up largely in passing in Anna's lectures. There are very big benefits that can come out of them. Is there a question before I?
Does the order matter here, like mu square and g, the limits which you did?
So G, we don't have to worry about tuning that to 0. That's the one that decouples. And yeah, there is, the order of limits is a good question to ask, that formally we have to take the volume to infinity, we have to take the continuum limit before we are allowed to take the deformation parameter exactly to 0. What I do in practice in these numerical calculations is I make this mu squared actually proportional to A over L so that they essentially vanish along the same line. So approaching the continuum limit then removes the scalar potential and restores the moduli space all in one go. And at least for the purposes of the calculations that we're doing at present, that's sufficient. Okay, I guess I have 5 minutes left, so that should be enough to get through a couple more things. So a quick look at more of these word identity violations for the improved and that unimproved action. Here, looking at different values of n. So previously, it was just 2 color theories and about as far away from the large n-planar limit as we can get. A question came up on Monday about what sorts of n numbers of colors we're able to look at. In 4 dimensions, we've not really gone beyond 4 colors. One thing that is nice is that larger n also reduces the violations of this word identity. I think that's just because there are more degrees of freedom floating around in the system. So it's even on smaller volumes, it feels a bit closer to a continuum limit just by virtue of having more degrees of freedom. But empirically, there's a nice linear dependence on 1 over n squared that is also obviously improved by this improved action compared to having everything in a supersymmetry breaking, implemented in a supersymmetry breaking way. One question that might have come to your mind was, well, if we have this procedure to lift these flat directions supersymmetrically, why don't we do that for all of them, both the SUN flat directions that have been in this supersymmetry breaking potential, as well as those U1 flat directions associated to the plaquette determinants? Well, we tried it, and what we tried didn't work, whether that's because of some fundamental obstruction or because Simon Catterall and I working on this are insufficiently clever remains to be seen. The issue that we got was then when we had both of those deformations in that same site operator O coming into this deformation, we had to make sure that those 2 pieces, the SUN sector and the U1 sector, couldn't cancel each other off, that same dynamics where one of them goes off to a very large positive value, another goes off to a very large negative value. The overall constraint is satisfied, but the flat directions are showing up in that correlated way. In order to avoid that, we had to essentially make the constraints positive definite, which then required that they had to be satisfied actually lattice site by lattice site. So there were so many constraints that the system was, despite having an exactly supersymmetric lattice action, it was unable to find a field configuration that satisfied supersymmetry, that had that obeyed the word identities. What came out was actually word identity violations that were worse than this improved action that had the explicit scalar potential breaking the supersymmetry. And in particular, we lost a nice approach to the continuum limit, probably because the word identity violations here are no longer coming from that soft SUSY breaking with a tunable parameter, but they're coming from having too many constraints that the system is not able to simultaneously satisfy. So this is something we tried, didn't work, could be worth thinking about. The more clever folks out there can come up with a more functional way of implementing this. Simon has continued to think about this question in recent work from a couple of years ago that I wasn't involved with, where instead of complicating this Q-exact deformation to include more things, actually simplified it to include less stuff and retaining or restoring that SUSY breaking potential for the SUN sector, going back just to the U1 sector in the Q exact deformation. But instead of having the plaquette determinant, trying to work in terms of the determinant of an individual link rather than a plaquette. So this is still sensitive to the U1 sector. The reason we didn't work with it in the past when I was involved was because it's not gauge invariant. The link transforms with one gauge transformation at one site on the right-hand side and a gauge transformation at a different site on the left-hand side. So this action is violating gauge invariance. It is doing that in the U1 sector. And the argument in this work is that maybe this U1 will decouple in the continuum, so we don't have to worry about breaking gauge invariance here, so long as we don't explicitly break it in the SUN sector. Given the big effects of the U1 sector and things like monopole condensation that we see to motivate these deformations in the first place, I'm not yet convinced by that argument, but it's certainly something that is worth considering, especially because the empirical results that come out of this work look reasonable and have the advantage that they're able to get to much stronger lattice Tooft couplings of order 30 beyond the self-dual point for this two-color system. That's much stronger than the improved action is able to reach. And the reason the improved action has trouble is due to that sign problem, or at least related to that sign problem, which will be a good thing to come into in the next lecture. I'll just end by, yeah.
Previous slide.
There we are.
Yeah, so can you comment on generalizing this to n color system from two color system? I mean, can we go to lambda light equal to 30?
So the people to ask are not me, but I was talking about this with Goksu Toga at the Lattice conference earlier this month. And what he was telling me was that at the time of this paper, it only worked for two colors. And any attempts to run numerical calculations with this gauge dependent deformation for a larger number of colors broke down for obscure reasons. And for reasons that I don't know, that has been improved over the past 2 years, and they now have SU3 results. I don't know if larger numbers of colors are possible. Hopefully, the lattice proceedings from Goksu's presentation will answer that question when they come out at some point in the next few months. I will wrap up for today. I'm over time. I want to say we've gone a bit more slowly than I expected, but that's in part because this twisted n=4 lattice system is fairly complicated. And I've tried to reveal what's going on sort of under the hood to give an appreciation for what's involved in these lattice calculations. This is what the lattice action looks like once we have all those deformations in place. There's something like 100 data transfers every time we have to act with the fermions, act with the Dirac or the fermion operator, the analog of the Dirac operator. So this is much more computationally expensive than something like QCD by orders of magnitude. And so in order to reduce some of the barriers to entry, all of the code development that we have for this system is publicly available on GitHub with a user guide that is in the process of being updated, because this software is being actively developed for some of these new applications and also performance improvements, and can be a way for those of you who are inclined to do things like look at the boundary conditions to do so. It's a nice code, it scales as it should with the number of colors, with the lattice volume. That's all I'm going to say for today, and I'll figure out what I'll cover in the third lecture when we get there. So we have, I'll end there, take any more questions, and then wrap up tomorrow morning.
All right. Thanks, David, for a nice lecture. Time for questions. Yeah, Navdeep.
The difference in this new work by Goksu and the previous one, is it only the scalar term?
Yeah, that's, I believe the only change they make is what do you choose for that operator there?
So 2015 work had scalar term also, the mu square v.
Yeah, that scalar potential. Scalar potential is the same from 10 years now, from before I started working in this field. And it's all about the U1 sector that is more challenging. And there's a story I can tell about why U1 seems, or why U1 is more challenging than SUN. Maybe I can leave that for the end of today if there's interest in it.
Thank you.
More questions?
We had a good number as I was going through. So.
Okay, all right. So if there are no more questions, let's thank David again.